Hey guys, how are you? I'm so glad you're watching this. We're going to be talking today about how you name ionic compounds. An ion is an atom or group of atoms that have a charge. You should write that down. Neutral atoms have an overall charge of 0. What that means is your protons are equal to your electrons. If an atom loses an electron, so think of this, you get rid of something negative in your life, you become more positive. Same is true with atoms. They get rid of electrons, they become positive. They have a specific name, it's called a cation. So if an atom gains an electron, takes up something negative, so keep in mind, there's an electron that's just been released from a cation, if you will, ejected from a cation. If an atom absorbs that electron, it gains an electron, it takes up a negative charge, it becomes more negative. So it's kind of counterintuitive. You're losing something, yet you're becoming positive. Okay? As you're getting something negative, you are becoming more negative, and the term for that is anion. The cations are going to be in red, right here. The anions, things that are becoming more negative, gaining electrons, are in blue. One other thing, just to recap, valence electrons, doesn't matter where they are, and electrons in general are always negative. The protons and the neutrons are not going to be involved with the development of charges at all, positive or negative. Ionic compounds, this right here. So if you ever use this for anything, it's an ionic compound. Okay? And more specifically, it means there's a metal and a non-metal involved. So think about this. There are exceptions in chemistry. You know, every rule has an exception. But please remember that the metals, when we say ionic compounds, we're talking about metals and non-metals. And the metals are red. The non-metals are blue. So if you don't quite remember how this works, I'll fish out a periodic table to show you. I'm going to set it right here so we can take a look at it. The metals are all over here. 80% of the periodic table are metals. And the non-metals are to the right of the staircase. So you've got the staircase and the non-metals are to the right of it. So again, 80% are metals. The non-metals are over here to the right. So let me just repeat. The blues are the non-metals. The reds are everything to the left of this. And those are the metals. The exception, of course, is hydrogen. Hydrogen is placed in the group 1, and so that is a non-metal. Now, the phrase I need for you to remember is red, white, and blue. You got it. Perfect. Red, white, and blue. The red always comes before the blue. So whenever you're writing formulas, this is very important. This, the red, whatever's on that card is always going to come before the blue. You cannot flip them around. So there are two things you're looking at when you're looking at these cutouts, both the red and the blue. The first, the loss or gain of electrons from the atoms concerned. And the second is how many atoms are involved in the formula. So that's what I'm going to dwell upon. And you're going to hear me repeat this again and again. And I'm going to walk through a series of examples. So the very first example is sodium chloride. So on a test, on a quiz, you're going to see something like this, and it's going to say sodium chloride. So when you see that, super important that you are focused on this right here first. Okay, and that is probably going to be red. Why? Not probably, it is going to be red. The important thing is you recognize that there's a metal in there. Okay, so sodium chloride. Sodium is a metal. We're talking right now about the cutouts. And I'll explain what binary compounds are in a minute. But sodium is going to be red. So let me get my glasses on anymore. I can't do it without these glasses. So I'm looking for sodium, and here we go. So I've got my clip. I set the sodium right here. Okay, and the next thing I need is chloride. Now, chloride, when you look at this, refers to chlorine, but chlorine that has gained an electron. So I'm going to grab these two. These are the red and blue cards that I have. Here's the sodium. Here's the chloride ion. So we've got these two. We're going to start working with them. So step one is you're going to unclip these. And you're just going to lay it out here. So remember, you've got a total of 3. So you just unclip the extras, lay the sodium out, lay the chloride out. Okay, and you want them side by side, and that's good. So you realize that it's sodium chloride, and that is what we have here. So that's excellent. So we've got this, we've got this, we've got this. Works. Next step, we're going to flip these over. So let me just grab this and flip this over. That's sodium. And I'm going to get the second component, which is the anion. Let's line them up perfectly. Sodium chloride. Okay, so this is the first step in the process of learning how to write an ionic formula, or formulas in general, and specific class ionic formulas. So you need to have these cards set up where you can find them quickly. You need to have them clipped, otherwise this is going to take you incredibly long. So having these clips on these cards makes a lot of sense. Now, once you have this on, this is what you need to do. Okay, you need to look at this and ask yourself what's going on here. So I'm going to walk you through this in terms of writing the formula first. The sodium is a cation. It has a charge of +1, and the size of this cutout is the smallest. The chloride ion is a -1. It is right here, and we are going to ignore the charges. So let me just cover that up real quick. Let me try and see. Let's see if I can do this effectively. Boom. So you are not interested in the charges when you're writing formulas. So this might be, there we go. Sodium done. We're ignoring the charge for now. I'm going to repeat this with the chloride ion. So let me just cover that up as well. Please understand, guys, I'm kind of doing this on the fly, but the goal is you be able to see that. So I think I have that set up just right. So you got the sodium ion and the chloride ion. We do not care particularly about the charge for now. So we're going to ignore the charges that are under these strips of paper. We only care about the Na and the Cl. You do not put the 1. And the reason you don't put the 1 is because in chemistry, if you have the number 1 as a subscript down below, you never write it. It's assumed that that's like in math. You don't write an exponent of 1. So even though there's one of these, you don't write the 1. Okay, now let's look at the chloride ion. Same diff with the chloride ion. It's right there. The Cl, there's only one scrap of blue paper, so we're going to write that next to it, Cl. Boom. That's your formula. The next thing I need for you to do is actually draw these boxes. So you got the formula, but I need for you to draw these boxes on the paper. So I'm going to pull this down, and I've just drawn these boxes in advance so you can kind of take a look at it. That's the Na plus right there, and that is the Cl minus right there. So these boxes are drawn. So this helps you kind of learn to craft the formula, which is NaCl. So we're going to do another one now in a second. The second one is going to be copper chloride. So you've seen the chloride ion before. We'll leave that right there. And I'm going to get, and this is copper 1. So we got to make sure that we get copper 1. We lay the copper 1 there. And let's just flip the chloride ion over. We've got copper 1 chloride. You draw these out and color them. And again, we are going to ignore the charge. So you're not particularly concerned with the plus or any number that is a superscript. You are completely ignoring that. Let me go ahead and cover up the chloride ion. And I'm not going to do this for everyone, guys. You kind of need to remember this. So you are ignoring the charge. The numbers that are on the top, you ignore them. So that formula is going to be copper. You ignore the 1, chloride. Boom, beautiful. Again, please remember, if you flip the blue and red, so you give me the anion first, you get a 0. Big fat goose egg, it's got to be red and then blue. So copper chloride, there's the formula. There's 1 copper, there's 1 chloride ion. Okay, now let me just talk for a second about the question about electrons. When you see these cards, what you need to immediately be thinking about is, okay, we've got a metal, we've got a non-metal. So there's 2 things going on. Let me point them out to you. That's the copper. It is losing 1 electron right here. That is why it is +1. The chloride ion is gaining 1 electron and only 1 electron. So that becomes negative. So the plus and the negative, the plus and the minus, represent the size of the card, but they also represent how many electrons are being lost and how many electrons are being gained. So the fact that it's only losing one represents this size. The chloride ion is gaining one, so it's in blue, and it is also a small size. You're going to see something slightly different now. So we're going to look at the next compound, which is copper 2 chloride. So what I highly recommend this. See if you can kind of follow along with me and actually do these while I'm doing it as well. So hit pause and let's get these parts together. So the chloride ion, but this time we are not looking for copper 1. We are looking for copper 2. This becomes really important. Please note, copper 1 and copper 2 are different sizes. So you cannot just pick up any old copper. You have to look at the Roman numeral that's given here to decide which one of these two you're going to use. The third example here is copper 2 chloride. So what we do initially, you grab the copper 2, unclip it, set that on the side, and bring in your copper 2. And this, at this point, you should know, is the chloride ion. So it's chlorine that has gained an electron. So copper 2 chloride, you're good to go. The only problem is you have a gap over here. You cannot have this gap. You've got to have this filled up. And what that requires is a second chloride ion. So let's slide that in here real quick. So you got the second chloride ion. So you've got copper 2 and you've got 2 of the chloride ions. So you've got 1 scrap of red paper, 2 scraps of blue paper. Let's flip it over. That's copper 2. And I'm going to get the chloride ion sitting right next to it. So now we know that we've got the right chemical, the right cards for the chemical, because the cation said copper 2, anion said chloride. We've lined them up. We're going to draw this right here. We're going to color it in. So I'm just going to do this really quick. This is the red one. Okay, so this is the cation. Now guys, when you're doing this, I highly recommend that you do it fairly neatly and you do it clearly. Just remember, I'm kind of filming this and trying to do this at the same time. So that's the that's the cation. These are the anions, and there are 2 of them. Okay, please remember, you are not concerned with the charge. So you are ignoring this charge right here, this and this. The charges do not in any way compute when you're writing the formula down. Very important to remember. So I'm going to write this formula down. Here we go. So how many scraps of red paper? There's 1 scrap. So you're going to write copper. Now this is different from copper 1 chloride. You've got 2 scraps of blue paper. So you have to account for the 2 scraps, 2 bits of blue paper, and you write Cl. And because it's a number other than 1, you've got to actually put the 2 in there. So you do not write the 1, but you must write the 2 representing these 2 ions right here. Okay? Let's keep going. Another example for you. We've got copper 2 oxide. We are going to get rid of the chlorides. So I'm going to move those off of here. That's copper 2 oxide. I got that from my stack of cards, which are lying right here. So copper 2 oxide, we're going to flip this over. Okay, step 1 is you got to draw these. You got to color them. Okay, so here we go. Same deal. The oxide that I'm coloring in here is only 1 card, but it is a larger card. It's the medium-sized cards. It's double the size of the chloride ion. What that means is that both the electrons are going from the copper. They are making their way into the oxide ion. Okay, so you've got 1 of each. We're going to write the formula first. So how many scraps of red paper? Right here, there's 1. And how many scraps of blue paper? Please remember, we are ignoring the charges. So that would be copper O. There is 1 scrap of copper, and there is 1 scrap of the oxide ion. So in this example of copper oxide is losing 2 electrons, and there is space for both those electrons that are being lost in 1 atom of oxygen. You don't need 2 atoms because the 1 atom of oxygen can absorb those 2 electrons that have been ejected by the copper 2. Right here, this absorbs it. That's why you just need 1 of each. Please remember, your goal is to always line these up perfectly so that they fit. Most of you guys watching this and gals really get a feel for this as you put these together. So please actually put these together. So this is iron 3, and the oxide, we already have that out, sits like this. Now, you cannot have this gap here. That's not allowed in this process of learning how to write formulas. So you must fill that in. Here's what you do. And remember, you can't just put something else in. You have to put another oxide if there's a gap for an oxide. So we're going to stick the next oxide in. Now we've got a problem. There's a gap on the cation side. So let's grab another iron. So again, you got to make sure it's iron 3. It can't be just any old thing. It has to be iron 3. And we're going to stick that in. Okay, now there's still a gap here. So we're going to come in with another oxide, and voila, beautiful. Look at that. That is perfect. So I'm going to flip the cards over. So we've got iron 3, 2 iron 3s. I've got the oxides over here. Bada bing, bada boom, we're almost done. So let me flip these guys up, and here we go. Now, this is a little bit difficult, so please pay attention. You ignore all these charges. So I've been saying that. So you ignore anything that is a superscript. This is a superscript, ignore it, ignore it, ignore it. 3 plus, ignore it, 3 plus, ignore it. We are interested in only counting the scraps of paper or the bits of red and blue paper. That's all we're looking at. So we've got 2 bits of red paper. So we're going to write down iron, Fe. We ignore the charge, but we count the number of pieces of red paper. That's a 2. We then look at the oxide. And remember, oxide is nothing but an oxygen that's grabbed 2 electrons. So the oxide, there's 3 of them. So that means there's 3 atoms of oxygen. We are not concerned at this point with what the charges are. So we ignore the charges. We write the O, and we count the scraps of blue paper. Put the 3 there. Voila, we're set. So let's take a look at the iron 3 oxide, what it looks like when you draw it out. Again, it's Fe, 2 of the irons here. Again, this is not to scale, guys. I just made this up so it's somewhat easy for the camera up above to capture it. There's iron 3, and there's 3 oxygens. Okay, so again, I want this colored in, so I'm going to do this pretty quick. Iron 3, those are colored in. And let me get the 3 oxygens. Now, while I'm coloring this in, let me just tell you really quickly what's going on here. The iron, right here, is losing 3 electrons. 2 of them end up getting sucked into the top atom of oxygen. So it's gotten rid of 3. 2 go here, 1 goes here. Now, this one's going to lose 3 as well. And voila, here you go. 1 goes in here, 2 go in here. So the electrons are balanced out. You can't have a 1 electron kind of just hanging out. They all have to find a home, and they all have to find homes in the same types of atoms. So you can't put a chloride in here or something like that. They all have to go into oxygen atoms. They all have to have a charge of 2 minus. The last one is going to be sodium oxide. In this case, we flip it. So again, you should be familiar with sodium at this point. It is like so. That's sodium. And we're going to get the oxides. We've been using the oxides quite a bit. So I'm going to get you the oxide right here. Voila. In this example right here, you have a gap on the left side with the cation. That is not going to work. So we're going to have to get another sodium. Okay, so we're going to try and plug these in so they even out. So they are even right here and right here. Okay, so these 2 are here. Boom. 2 sodiums and an oxide. So let's flip the sodium over. So that the Na plus is next to an O2 minus. We're going to draw this. Here we go again. Isn't it amazing that I've got all these drawn out already? Maybe I should have colored them too. Okay, so in this example, let me just talk about, while I'm coloring this, the sodium is losing 1 electron and it goes into the oxide. The problem is the oxide, or the oxygen atom, isn't happy with just 1 electron. So it needs the other electron for this to work. And so that is why you end up with 2 sodium atoms right here. And they are losing, this one's losing an electron, this one's losing an electron, but they are both going into just 1 single oxygen atom. And why is that? Because the oxygen atom has a place for two electrons, not just 1. So 1 from here, and they both make it into the same oxygen atom, and of course it becomes oxide. I'm going to write the formula for this. So there's 2 scraps of red paper. Let's take a look here, guys. So there's a sodium and a sodium. So again, ignore the charge. So we are not interested in the charges at all. So we're just counting the scraps of red paper. So there's 2. So it's Na2. And now you've got the oxygen, and that is, there's only 1. There you go, Na2O. That is the formula for sodium oxide. Hope you found this helpful. We'll pick up another set of compounds that are more complicated in the next video. Bye.